Good morning, students. Myself Parvishuk Sare, lecturer in MTT department. Now, the class revision class, that is electronic control. The study about electronic control. Here, the first question: define semiconductor. What is meant by semiconductor? A semiconductor is a substance which has resistivity in between conductors and insulators. Example: silicon, carbon, selenium, germanium, etc. Next one, list the characteristics of semiconductor. Here the characteristics are: the resistivity of a semiconductor is less than in an insulator but more than a conductor. A semiconductors have negative temperature coefficient of resistance. This resistance of a semiconductor decreases with the increases in temperature and vice versa. When a suitable metallic impurity is added to the semiconductor, its current conducting properties changes. That is the characteristics of semiconductor. It is most important in your exam purpose. Next question, explain intrinsic semiconductors. Here the intrinsic semiconductors, here the positive electrons and holes are created in normal temperatures. Here in this diagram the holes and free electrons, okay, that is the procedure. Are a semiconductor in an extremely pure form is known as an intrinsic semiconductor. Means what? There is no any add the material, it's only pure form. In an intrinsic semiconductor, even at room temperature, whole electron pairs are created. When electric field is applied across an intrinsic semiconductor, even at room temperature, whole electrons pairs are created. Even at room temperature, example 25 degrees Celsius, 22 degrees Celsius, 28 degrees Celsius, like that. When electric field is applied across an intrinsic semiconductor, the current conduction taken place by free electrons and holes as shown in figure. The free electrons are created due to breaking up of some covalent bonds by thermal energy. At the same time, holes are created in the covalent bonds. Holes being positively charged moves towards the negative terminal of supply. As the holes reach the negative terminal B, electrons enters the semiconductors. Crystal and combines with holes, and thus holes are concerned at the same time loosely held electrons near the positive terminal are attracted away from their atoms into the positive terminal. This creates holes which again towards the negative terminal. Next question. Explain the intrinsic semiconductor. Explain the intrinsic semiconductors. When a small amount of impurity is added, extrinsic semiconductor is pure form, but here some impurity is added to a pure semiconductor. The resulting material called an extrinsic semiconductor. Intrinsic semiconductor is a pure form. Extrinsic semiconductor is impurities added. The process of adding impurities to a pure semiconductor is called doping. The amount and the type of such impurities to be closely controlled during the preparation of extrinsic semiconductor. Generally, for 10⁸ atoms of semiconductor are extensively used in the manufacture of diodes, transistor and microprocessors. The purpose of adding impurity is to increase either the number of free electrons or holes in the semiconductor crystal. Extrinsic semiconductor, there are two types. First one, N-type semiconductor. Second one, P-type semiconductor. Here, sketch and explain N-type semiconductors. Here in this diagram, silicon and free electrons. In middle, the extra holes, free electrons are created. That is N-type semiconductor. Okay. In this time, the donor level, the conduction bond empty or partially filled. That is band gap. Here the free electrons are arranged in this N-type semiconductor. When a small amount of pentavalent impurity is added to a P-type semiconductor, it is known as N-type semiconductor. The typical example of pentavalent impurities are arsenic and antimony and phosphorus. It consists of 5 free electrons and it donates free electrons to a semiconductors. Hence, the impurities are called donor impurities as shown in figure. From this circuit diagram, it is clear that number of negative charged free electrons attracts towards the positive terminal, constituting electric current. The current conduction in the n-type semiconductor is predominantly by free electrons, that is negative charges, and is called n-type electron type conductivity, that is p-type semiconductor. Sketch and explain p-type semiconductor. Here in this area, n-type semiconductor is extra electrons is there, p-type semiconductor is one less electrons is there, that is the hole is there, that is trivalent impurity atoms. It is called a trivalent impurity atoms. When a small amount of trivalent impurity is added to a pure semiconductor, it is known as p-type semiconductor. The typical example of trivalent impurities are gallium and indium. It consists of 3 free electrons and it accepts free electrons from the semiconductor. Hence, the impurities are called acceptor impurities as shown in figure. From the circuit diagram, it is clear that number of positively charged holes attracts towards the negative terminal, constituting electric current. The current conduction in p-type semiconductor is predominantly by holes, that is positive charges, and is called p-type or hole type semiconductor. Next question, make use of sketch and explain positive negative junction diodes. Here the positive electrons and negative electrons there in this diagram. Explanation is, it is two element semiconductor device formed by joining the p-type semiconductor to a piece of n-type semiconductor. Join is called the p-n junction. p-n junction diode has p region with more number of holes, that is positive charges, and an n region with more number of electrons, that is negative charges. Due to this difference in the concentration of holes and electrons and due to thermal energy, certain holes diffuse into n region and combines with electrons, and certain electrons diffuse into p region and combines with the holes. Due to this, potential barrier is set up across the junction. An important characteristics of p-n junction diode is that It allows current to flow in only one direction, that is the forward bias. During reverse bias, it acts as an insulator. Next question: make use of sketch and explain Zener diode. Here, the Zener diode is cathode and anode, that is current and voltage, that is forward bias and reverse bias region. Here, when a diode is reverse biased, the critical voltage is reached, that is as breakdown voltage, and the reverse current increases sharply. This is found by Zener. Hence, the breakdown voltages is called Zener voltages and current is called Zener current. A properly doped crystal diodes which has a sharp breakdown voltage is known as Zener diode. The symbol and typical characteristics of a Zener diode is as shown in the figure. Until the reverse bias reaches the breakdown voltages, the current is very small due to leakage current. When the breakdown occurs, heavy current flows through the diode and the voltage remains constant at the breakdown level. Zener diode has following characteristics. A Zener diode is like an ordinary diode, except that it is proper open so as to have a sharp breakdown voltage. A Zener diode is always reverse connected, that is, it is always reverse biased. When forward biased, its characteristics are just like an ordinary diode. The Zener diode voltage remains constant even when Zener current increases considerably. Next one: sketch and explain thyristor. Thyristor, SCR, silicon controlled rectifier. It's called as silicon controlled rectifier. Thyristor, when a PN junction is added to the junction transistor, this resulting 3-junction device, and such a device is called silicon controlled rectifier or thyristor. The construction of silicon controlled rectifier is as shown in figure. It has 3 terminals, namely anode, cathode and gate. Outer p-type material is connected to the anode. N-type material is connected to the cathode, and third from base of the transistor is connected to the gate. That is 3 types of connected. Here the 2 types of silicon control rectifier, one reverse bias and another one forward bias. First one, reverse blocking mode are positive negative junction J1 J2 J3. G is a gate, anode, cathode, positive negative electrons flowing. Here in this explanation is, in this mode the silicon control rectifier is reverse biased by connecting its anode terminal A to negative end and the cathode terminal K to the positive end of the battery. This leads to reverse bias of the junctions J1 and J3, which in turn prohibits to flow the current through the device, in spite of the fact that the junction J2 remains in forward bias condition. In this state, the SCR behaves as a typical diode. In this reverse biased condition, only reverse saturation current flows through the device. As in the case of the reverse biased diode, which is shown in the characteristics curve by blue line, that is, the device also exhibits the reverse breakdown phenomenon beyond a reverse set voltage limit, just like a diode. Next one, forward blocking mode of silicon controlled rectifier, that is positive negative J1 J2 J3 junction. G is a gate, anode and cathode, that is forward blocking mode. Here in this diagram, the positive bias is applied to the silicon controlled rectifier by connecting anode terminal A to the positive and cathode terminal K to the negative terminal of the battery, as shown in figure below. Under this condition, the junction J1 and J3 get forward, while junction J2 reversed biased. Here also current passed through the thyristor accepts any current flowing as saturation current, as shown by the blue curve in the characteristics curve below. That is a upper one forward biased, down one reversed characteristics, and holding the current I and voltage V, that is forward break over voltage and reverse break down the voltage. That is the graph of the forward and reverse blocking modes. Thank you one and all.